In this lecture, we will discuss the T wave, specifically what it represents and how it should normally appear on the EKG. The T wave is the next positive or negative deflection after the ST segment, and it represents ventricular repolarization. So if you look here, we have our T wave. So this is our P wave. That's atrial depolarization. We have ventricular depolarization. This would be our ST segment we talked about, okay? And then our T wave is this here, okay? And that represents ventricular repolarization. Now there are three portions of the T wave that I want you to be aware of. The early portion of the T wave, the late portion of the T wave, and the end of the T wave, okay? And you can see them here, early, late, and end, okay? Now the early portion of the T wave represents the absolute refractory period. This is the time in which more ventricular cells are depolarized than repolarized. And because of this, the ventricular cells will be refractory to any new impulse. So if you look here, the early portion would be from the beginning of our T wave to about this portion, okay? So that's the part where this is absolutely refractory, meaning that we have more depolarized ventricular cells compared to the repolarized, and because of that, it was not able to take any new impulse that comes down through the conduction system, okay? Then there's the late T wave, and this represents the relative refractory period. This is the time in which more ventricular cells are repolarized than depolarized. And because of this, the ventricular cells are now ready to receive a new impulse, okay? So that would be probably from about this point here up until here, okay? That's that late portion of it, okay? And it's now we have more repolarized cells, and because of that, we're ready to receive the next impulse that comes down the conduction system. And then we have the end of the T wave. Okay, so this portion right here, right at the end of the T wave, and this is sometimes referred to as the supranormal period or hyperexcitable period, in which even a weak stimulus can initiate an action potential. Okay, so everything's pretty much repolarized, all the ventricles, and even a weak stimulus can come down that area and cause an action potential to go about. Okay, now let's look at the orientation of the T wave. Interestingly, the repolarization wave should have the same orientation as its corresponding depolarization complex, okay? And this seems strange, doesn't it? We are saying that both ventricular depolarization and repolarization normally appear to have the same orientation on the EKG, okay? Remember, here's our ventricular depolarization wave, and this is our ventricular repolarization wave, or T wave. Notice that they're both mostly upwards, okay? Do you remember when we talked about atrial depolarization, the P wave, and atrial repolarization, the TA wave? They go in opposite directions, okay? We were saying this would be atrial depolarization going up, and then if you had a repolarization wave, often you don't see it, but if you were to see it, it would be going the opposite direction, okay? So this is something different. Here we're saying that the ventricular depolarization, the QRS complex, and the ventricular repolarization, the T wave, are normally going in the same direction. So let's see why this is the case. Now, during ventricular depolarization, the impulse moves from the endocardium to the epicardium, leaving the subepicardium positively charged. Therefore, the subepicardial area appears positively charged to the electrode and will show up as a positive QRS deflection. Okay? So if you look here, this is our ventricular wall, where this is the endocardium, the inner layer, the epicardium, and notice that our depolarization wave is moving from left to right, and here's our positive end. This right here is our electrode, okay? And what that electrode sees is this positive end. And because of that, we have our QRS complex that is going up, okay? Now with ventricular repolarization, this wave moves from the epicardium to the endocardium. That is, it goes in the opposite direction. So you will have a subepicardial layer that is positively charged, and therefore it will register as a positive deflection on the EKG. In other words, we'll have that upright T wave, okay? So we're saying now the ventricular repolarization, what's going on here, it's going in the opposite directions. It's heading this way, okay, from right to left. And because of that, it's a negative wave moving in that direction. This part of it is positive, okay? And what the electrode sees is this positive charge. And because of that, it will be upright, okay? So that's one thing to note. With these ventricular waves, the depolarization and repolarization, they're going in opposite directions. Whereas when we talk about the atrial waves, they actually go in the same direction. Hopefully this makes sense, okay? Remember, we said with atrial depolarization and repolarization, the waves travel in the same direction, whereas here with ventricular depolarization and repolarization, they travel in opposite directions. Okay, let's look at the morphology of the T wave. Normally, it should be asymmetric, with the beginning of the wave rising and falling slowly, and then the end of the wave rising or falling more rapid. So let's erase some of this here so we can see what we're talking about with our T wave. Okay, and notice you can see this early portion of the T wave, we have a slow upstroke, okay, our upright T wave, right? So notice how this slope is like this, okay, and then that latter portion of the T wave has a fast downstroke, okay? That slope is much steeper on the other side, okay? If you notice, that's an asymmetric T wave, okay, and we'll talk about that now. So how do we assess for T wave symmetry? Well, the first thing you want to do is find the peak of the T wave and then draw a perpendicular line from the peak to the baseline, and then finally compare the two sides for symmetry. Asymmetric T waves are considered normal, while symmetric T waves are considered a sign of pathology, such as myocardial ischemia. So let's look at this. How do we find them? So notice look right here. We have our T wave present here, and notice we're going from the point or the peak of it. We're drawing a line straight down to the baseline, and then we draw the lines that are connecting it, okay? And notice we have this line that goes up this way and this way. So this is an asymmetric T wave, whereas if we look at the one below it, so again, here's our T wave. Again, we'll draw a line or perpendicular from the apex, the top of it, to the baseline, and then from that, we draw our lines to the peak of it, right, the slopes, and notice that this side is the same as this side, okay? They are symmetric, and we said symmetric is abnormal and a sign of pathology. Now, the T wave may also be biphasic, broad, or peak under other circumstances. In terms of the T wave axis in the frontal plane, it is normally between negative 30 and positive 105 degrees, directed leftward inferiorly and often anteriorly in adults, just like the QRS axis. In other words, the QRS complex and the T wave generally have the same polarity. Oftentimes, the T waves will be upright in leads 1, 2, V3 through V6, and they'll be inverted in AVR, and sometimes even lead V1. The other leads tend to be variable. Now, with the T wave amplitude, in general, the limb lead should have an amplitude of 6 millimeters or less, while the T waves in the precordial leads may have an amplitude of up to 12 millimeters. The greatest amplitude tends to be in leads V2 and V3. Some have also suggested the T wave amplitude should be less than 2/3, but greater than 10% the amplitude of the R wave. And lastly, the T wave amplitude appears to be slightly less in females than in males, okay? And it seems to decrease with increasing age. So as we get older, the T wave amplitude tends to go down. And when we talk about amplitude, we're simply talking about the height, okay? So let's just erase some of this here. When we talk about the amplitude, it's this portion here, okay? That's our amplitude of the T wave from the top of it, the apex, to the bottom. Okay, so let's briefly review what we discussed before we end here. So again, the T wave is the next positive or negative deflection after the ST segment. Okay, we said this is our ST segment, then here we have our T wave. Okay, we talked about this being the T wave being ventricular repolarization. Three different aspects of the T wave: the early portion where we have the absolute refractory period. Okay, in this case, we can't receive a new impulse. Okay, we're refractory to it. But then, as more cells become repolarized in the ventricles, we reach that relative refractory period where now we're ready to receive a new impulse. And then the end of the T wave. Okay, you may hear it as the supranormal or hyperexcitable period, where even a weak stimulus can cause an action potential. We talked about the T wave orientation, saying that it's going in the same direction as the QRS complex because the repolarization wave travels opposite to the depolarization wave, right? From epicardium to endocardium, right? Depolarization wave went this way, and a repolarization wave is going in the opposite direction. That was different when we talked about the atrial repolarization, depolarization, where those go in the same direction. In terms of the T wave morphology, remember we talked about that slow initial upstroke, okay, right here, and then that latter portion has a fast downstroke. And what we said about that is that these asymmetric T waves are normal, okay? So slow upstroke and rapid downstroke, okay? We can also have that slow downslope, meaning that if we have an inverted T wave, okay, maybe an AVR and then a faster upstroke, okay? So that's normal, maybe in lead AVR where you have inverted T waves. Now the T wave axis in the frontal plane is between -30 and +105 degrees. So again, this would be -30 degrees, and this is +105 degrees, okay? This would be 0, okay? This is +90, plus or minus 180, and -90. All right, so again, you can find the axis, but again, this is the same as the QRS axis, all right? So leftward inferiorly and could be anteriorly directed. Now the T-wave amplitude, the limb leads, tends to be less than the precordial leads. Usually it's about 6 or less, okay? In the precordial leads, 12 or less. And then it tends to be the greatest in leads V2 and V3 in the precordial leads. In terms of, some say that the amplitude should be less than or equal to 2/3 of the R wave, but greater than 10% of the R wave. Remember, in males, the T waves tend to be greater than females, and then the T waves decrease in amplitude with increasing age. Well, that's the end of this lecture. We discussed the T wave, specifically what it represents, and how it should normally appear on the EKG. I hope you learned something.